This is the first video for lesson 8.3. 8.3 is all about giving real-world context to exponential functions. And there are two major kinds of real-world context for exponential functions, and they're called growth and decay. So the goal here is to understand the difference between the two of them and to be able to use them. So they both start with the same general form, y equals a times b to the x. The difference is for exponential growth, which we can see here, your b value is greater than 1. So it could be 2, it could be 3, 4, etc. For exponential decay, your b value is between 0 and 1. So it could be 0.1, 0.5, it could be 4 divided by 5, it could be 1/3. It just has to be between 0 and 1. So this is decay on the left, and we can tell that when you have exponential decay, your function is decreasing. The value is going down over time. And for exponential growth, your value is going up over time. So we're increasing. Okay, so there will be contexts where we will want to grow and where we will want to decrease or decay. Many real-world things can be modeled by functions like this that describe things growing or decaying as time passes. So here, our x-axis is time. So it's growing as time goes by, or it's decreasing as time goes by. Examples of such things or such phenomena include studies about population, bacteria, viruses, radioactive substances, electricity, temperature, credit payment. Those are just a few examples. So any quantity that grows or decays by a fixed percent at regular intervals is said to possess exponential growth or exponential decay. So here are the two general models. In both cases, your b value, or what's in parentheses, can be described as 1 plus r or 1 minus r. Plus r for growth, minus r for decay. R is the percent increase or decrease expressed as a decimal. So if it's increasing or decreasing by 20%, R would be 0.2. Your A value out front, which is not being raised by an exponent, is your initial amount. So it's the amount you start with before you grow or decay. X, your exponent, is time, because we said these are things that are happening over time. Then the part in parentheses, your 1 plus r can be called your growth factor. Your 1 minus r is your decay factor. So let's practice putting these terms to use. So in example 1, I'm giving you different equations. You're supposed to determine whether the equation models growth or decay, the initial amount in this scenario, and the percent increase, decrease, and the growth or decay factor. So we can do A together, and then I'll let you continue working on your own. So in A, our growth factor is 1.2. It's that part inside the parentheses. So growth factor is 1.2. I know it's growth and not decay because this value is greater than 1. I know the growth factor is always 1 plus r, which means r is 0.2, which tells me that my percent increase is equal to 20%. So it's growing by 20% each time. My initial amount is 50. It's that A value. So whatever this is modeling, the amount you start with, the initial amount, is 50. And we already said that this one represents growth, not decay. All right, so now try B, C, and D and E on your own, and then check back in for the answers. Here's the answer for part B. It represents exponential growth. The growth factor is 1.023, which means R is 0.023, so our percent increase when we move the decimal over 2 places, 2.3%. The initial amount is 234. On to part C. Make sure you've tried it before you check the answer. In part C, we have exponential decay because we are subtracting a value from 1. The decay factor, 1 minus 0.2, is 0.8. Our R value was 0.2, so the percent decrease is 20%, and the initial value is 5,000. On to part D. In part D, we have exponential decay because our B value, or the part inside the parentheses, is less than 1. Our decay factor is 0.65. We can then solve for R, or maybe you can just tell by looking at it, the amount you are subtracting from 1 is 0.35. If you can't do that mentally, you can solve for R, like I said. I did that right here. So 1 minus R, we know this part, is equal to 0.65. Subtract 0.65 from both sides and add R to both sides. You get R equals 0.35. So if our R value is 0.35, we convert that to a percent. We know the percent decrease is 35%, and our initial value is 40,000. On to part E. Make sure you've done that before you check your answer. In part E, we have exponential decay again. Our decay factor is 0.4. That means our R value is 0.6, so we have a percent decrease of 60%, and the initial value is 1,000. If you have questions on any of that, make sure you post it on Edmodo. On to the actual context. In example 2, a bank account balance B for an account starting with S dollars. So starting with S dollars, that means it's an initial amount, earning an annual interest rate R, and left untouched for N years can be calculated as B was our account balance, equals S, the initial amount, times 1 plus the rate of interest raised to the nth year. Find a bank account balance to the nearest dollar. If the account starts with 100, has an annual rate of 4%, and the money is left in the account for 12 years. So we said S is the initial amount, so that's 100. R is the rate at which it's earning interest, 4%. That needs to be converted to a decimal. Remember, R is always a decimal, so this is 0.04. And our N is the number of years, and that's 12. So now we just plug it into the equation. So B equals 100 times 1 plus 0.04 raised to the 12th years. So 100 times 1.04 is the 12th. And we're supposed to round to the nearest dollar. That ends up being about $160. Okay, so what is interest? When you leave money in a bank account, it earns interest. So the bank is essentially giving you money to encourage you to leave money in the bank. So in this case, this person went from $100 to $160. Now that's a really good return on your investment, putting in $100 and getting $160 at the end of 12 years. In reality, we usually don't earn that much at the bank, but this is an example of how interest works. Okay, on to example 3. In 1985, there were 285 cell phone subscribers in the small town of Centerville. The number of subscribers increased by 75% each year. So if that's 75%, we know our R value is going to be 0.75. And that happened each year after 1985. How many cell phone subscribers were in Centerville in 1994? Don't consider a fractional part of a person. Solve graphically, numerically, and algebraically. Okay, so we know, since this is increasing by a percent, that this is exponential growth. If this was increasing by 2 people each year, that would be a linear function because it's going up by a constant number. Here, it's going up by a ratio or a percent. So we know we're looking for something exponential. We know exponential functions look like y equals a times, instead of b, we've been using 1 plus r to the n. We already identified R. Let's think about A, our initial value. Does it give us an initial value? Yes. In 85, there were 285 cell phone subscribers. And we know 1985 is the initial because it says we're starting for every year after 1985. So our A value is 285. And then N is the number of years. So we have Y equals 285, 1 plus r, so 1.75, raised to the n. And remember, n is the number of years after 1985. We want to make sure we're clearly identifying these things. So the question is, how many cell phone subscribers were in Centerville in 1994? We can tell how many years that is after 1985. It's going to be the 9th year. So let's plug in n equals 9. So plugging that in would be solving, algebraically. So y, or the number of cell phone subscribers, equals 285 times 1.75 to the 9th. Now that comes out to be about 43,871. We had to round because you can't have part of a person. So that's solving it algebraically, plugging it into our equation. Solving it numerically would mean that we're looking at our table. Looking at the table, we can tell that this is being multiplied by 1.75 to increase. Multiplied by 1.75. So each time it's going up by a constant ratio. It's being multiplied by 1.75. We could do that same thing here. We can multiply 25,069 times 1.75, and we would get the same result. If we wanted to solve this graphically, we would create a graph. Now we wouldn't use 4 quadrants. Since this is a real-world scenario, we want to think about what our x and y axis would be. In this case, our x value is our exponent. That's the thing that's changing, and that's the number of years. We're not going to have negative years, so we can just stick to positive years. Our y value is the number of cell phone users. Well, you can't have negative cell phone users, so our y values are also going to be positive. So this is years after 1985, and we always want to clearly label our axes. The y-axis was number of cell phone users. Okay, and we could go up to, let's say, 10 years. I'm going to mark off 2, so 2, 4, 6, 8, 10. And looking at the numbers we have here, we're going beyond 25,000. We're actually going up to 43,000, so maybe we want to mark this off to 50,000. So 10,000, 20,000, 30,000. Oop, I made my marks a little too big. Let's try this again. 10,000, 20,000, 30,000, 40,000, 50,000. Okay, so this is 50,000 users, 10,000 users. So you could graph this on your calculator as you sketch this out. Okay, so graphing those points, we're starting at 500, and then it's not even reaching 1,000 in year 2. So this is going to be really low. Let's get something that would show up. Okay, 8,000 after 6 years. So let's try that. 2, 4, 6 comes out to be 8,000. 14,000 after 7 years, so about there. 25,000, that's going to be in the middle here. Okay, so our graph looks something like this. All right, and if we did this on a graphing calculator, we would be able to solve for the value by doing a value at x equals 9. And we would get that that point is about 43,871. That's how you solve graphically. And we do want to identify that this is, the units are people, or cell phone users. So there's about 43,871 cell phone users. All right, next up, there are practice problems. You should do these practice problems on your own and then check in on the answer. In number 1, our equation is E equals 1,310 times 1.1 to the t power. So we know that that's our initial value. I've marked that as A. We know we're increasing by 0.1 or 10% each year. So this is 1 plus 0.1 and then to the t power. For number 2, make sure you've done that and then check your answer. Here are the answers for the practice problems. In 1, your equation is E, student enrollment, equals your initial amount, 1,310, times the quantity 1.1 to the t. So 1.1 is 1 plus your r value. In number 2, you have n equals 2,573 times 1.92 to the t power. How many incidents were there in 2003? Well, if you plug in 7 for t, the number of years after 1996, you get about 247,485 incidents. Make sure you're labeling what it is you're finding. All right, then in C, you're supposed to graph the model or sketch it using your calculator. So it's good to make a table of values and plot this. Probably only need to go up to about 7 years. My y-axis, I went up to 250,000 with 25,000 being the scale. Once you have graphed the general graph and labeled your axes, then you can start estimating the year where there were about 125,000 security incidents. So you can put in the line y equals 125,000, then find the intersection. The intersection, rounded to the hundredths, has an x value of about 5.95. We could leave that as the number of years, or we could round up to 6. So we could say, let's see, is there space here? Let's do it in green. So about 5.95 years after 1996 is when you had about 125,000, or you could show that you know that that year is actually, let's see, if we're adding 6 years to 1996, it would be 2002. So that's about the year when we had 125,000 security incidents. Okay, final example here, example 4. One of the most common examples of exponential growth deals with bacteria. Bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells, thus doubling. For example, if we start with only 1 bacteria, which can double every hour, by the end of the day we'll have 16 million bacteria. Gross. Okay, so here's a table of that. At the end of each hour, we're assuming that we're starting with 1 bacteria, so if we had hour 0, the starting value would be 1. And that would be 2 to the 0, which is 1. Then after the first hour, it doubles to 2. The second hour, it doubles 4. Again, it doubles 8. So it keeps increasing that way. If we do that after 24 hours, we had approximately 16 million bacteria. So we can tell that because it's doubling each hour, the pattern here is y equals 2 to the x. So does our exponential growth formula, would that give us the same thing? Let's think about this. If it's doubling every hour, the rate it's increasing by is 100%. So you're starting with 1, you end up with 2, that's an increase of 100%. If you start with 2, you end up with 4, that's an increase of 100%. So here, cross out growth rate, R is the percent increase. That's how we've been defining it. So using our model, y equals A times 1 plus R to the x. A is our initial amount. Well, we're starting with 1. That's our A value. We have 1 plus 100%. 100% as a decimal is just 1. So we have 1 plus 1 raised to the x power. And that's our time, the number of hours. That gives us 1 times 2 to the x, or just 2 to the x. So our growth model, or exponential growth, gives us the same as y equals 2 to the x. So we're actually not going to solve any problems with that, but we're just looking at two different ways to model this. In the next video, we will look at exponential decay and some special patterns for exponential growth and special patterns for exponential decay.